Hello and welcome to Perimeter Institute's public lecture series presented by Sun Life Financial Canada. My name is John Matlock, Director of External Relations and Public Affairs with the Institute. Greg Dick, your regular host and Director of Educational Outreach, is away tonight, a little bit under the weather, so we hope Greg gets well very soon. And meantime, it is my pleasure to thank you for attending on this chilly night and to welcome Ian Bancroft of Sun Life Financial Canada, our public lecture sponsor. The entire public lecture series all season long is made possible by Sun Life, so please join me in thanking Ian very much for your wonderful support. Now, a little bit about Dr. Robbert Dijkgraaf, someone we've been hoping to share with you for 3 years now. Dr. Dijkgraaf is Director and Leon Levy Professor of the Institute for Advanced Study in Princeton. His research focuses on the interface between mathematics and particle physics. In fact, Dr. Dijkgraaf is a mathematical physicist who has made significant contributions in string theory. Dr. Dijkgraaf is also a very strong advocate for science education, and he is a distinguished policy advisor. He is past president of the Royal Netherlands Academy of Arts and Sciences. In fact, that is the nation's leading advisor in science to the government. And he is currently co-chair of the Inter-Academy Council, which is a global alliance of many science academies that advises the UN and many other international organizations. For his contributions to scientific research, his leadership in educational outreach, his support of the sciences and the arts, and for his advocacy in the public policy space, Dr. Dijkgraaf was awarded the Spinoza Prize, which is the highest scientific award in the Netherlands, in 2003, a very high honor. And more recently, in 2012, he was named a Knight of the Order of the Netherlands Lion, and he is a member of the American Academy of Arts and Sciences and the American Philosophical Society. So tonight, he will take us on a rather mind-bending and interesting journey into the unreasonable effectiveness of quantum physics in modern mathematics. Please welcome Dr. Robbert Dijkgraaf.
Thank you. Good evening, ladies and gentlemen. What an absolute honor to be here and with such an enthusiastic and supportive and engaged public. So tonight I will actually take you through an adventure about the interactions of two of my great loves, physics and mathematics, and how they interact. And that's, of course, goes back down history. Not every application of mathematics was as successful as you see in this picture. And my title is actually taken from a beautiful essay written by Nobel Prize winner Eugene Wigner in 1960, where he talked about the unreasonable effectiveness of mathematics in the natural sciences. And it's a great article, and it starts actually with a little anecdote. And the anecdote is as follows. There's an owner of a shoe shop who's complaining that he never knows how many shoes and which size he has to have in his store. And then a mathematician comes and says, no, well, there's a simple formula for that. That's the Gauss distribution. And he shows the curve and the equation. And then the shoe salesman goes and says, well, all very nice, but what is this funny symbol here? Well, it's the Greek letter pi. What's that? Well, it's the ratio of the circumference and diameter of a circle. And then the shoe salesman says, what do circles have to do with shoes? And it's a very deep point. How does that Greek letter pi end up in that formula describing the world around us? It's unreasonable that mathematics is so extremely successful time and time and again. And at the birth of modern science, scientists actually were very much aware of this. Galileo wrote about the book of nature, and he described that it's written, philosophy, it was physics, is written in this grand book, the universe. And it's written in the language of mathematics. Its characters are triangles, circles, and geometrical figures. Euclidean geometry was, of course, almost synonymous with mathematics in that time, and without which it's impossible to understand a single word. One is wandering around in a dark labyrinth. And more recent time, Richard Feynman, famous particle physics, who actually wasn't a great lover of mathematics, but still he said, without those who do not know mathematics, it's difficult to get across a real feeling as to the beauty, the deepest beauty of nature. So if you haven't seen many mathematical equations in these talks, you're actually missing something. You have to understand the language. But on the other hand, Feynman also said, if all mathematics disappeared today, physics would be set back exactly 1 week. So I always thought that this is like, physicists win, until a very, very distinguished mathematician gave the perfect answer. He said, that was the week that God created the world. So my score is 2-to-1 math to physics. I think it's fine. But as it goes down further, this I always find a very emotional thing to show. This is a clay tablet from Babylonian times. It's more than 4,000 years old. And in it are written numbers. And one of these numbers is this number. It's an amazing large number, 343,768,681. Just remember 4,000 years ago, probably an engineer was walking around and understood this number. And why is it a special number? Well, it's actually a square of 18,541, which is itself a sum of 2 other squares. And of course you know what I'm talking about, it's Pythagoras. This was something that people used to measure land, to actually do engineering and physics. They knew these numbers were important. And actually, the old Greeks too were fascinated by mathematics. These are the Platonic solids, 5 perfectly symmetrical figures. And the Greeks actually thought these were very important. In fact, they thought that there is an association with the 4 elements. You know, the 4 elements, which were sometimes their idea of atoms, earth, fire, water, and air. And since there were 5 of these symbols, and 5 is 4 plus 1, they had an association. So for instance, earth was associated with little cubes, because you can stack them together. And fire, you can burn yourself, and it is indeed then given by this tetrahedron, this kind of pointy-shaped pyramid. And then turned out that there was one figure that couldn't be associated with any element. And that's the middle one, the dodecahedron. And then Plato said, well, perhaps this is the stuff out of which the heavens are made, the rest of the universe. It's the 5th element, the quintessence. And from that time, that figure, that beautiful figure, you see it back in art in all possible ways. Here from Leonardo, here by an Italian monk who was kind of the inventor of accounting, kind of very boring. But there's a little dodecahedron there to say, wait, I'm aware that there is more than just life on Earth. And artists of all life, form and shape, are using this figure. In fact, in the Dutch old hall of the House of Representatives, there is a dodecahedron. Not everybody captures the essence of that symbol, because in the Dutch newspaper it said, well, is it appropriate to hang a soccer ball in the... In fact, a few years ago, it was on the cover of Nature that perhaps our whole universe would have the shape of this dodecahedron. That would actually, we would be kind of moving in that space. It would be the ultimate vindication of the old Greeks. Unfortunately, as often with a good story, it was destroyed by more research. So now we think probably not. There are no of these structures. But they were in the minds, mathematics in the mind of physicists. For instance, here's the young Johannes Kepler, who was really obsessed with these figures. And when he was young, he built his first cosmology. He noticed that 5 plus 1 is 6. At that time, there were 6 planets orbiting the sun. And so you want to understand why these particular sizes of the orbits and the ratio of the orbits, can you explain them? And he had a model where he fitted the 5 figures into each other and their outer and inner orbits, and he got within 5% of the distribution of the orbits of the planets. Now, this you don't learn in physics books, because it was actually, well, there are many reasons, there are more than 6 planets, etc., and many other solar systems, but actually it was Kepler himself who destroyed this. Because he noticed, by looking carefully at the measurements, that the planets are not moving on circles, but on ellipses. Now, a circle is perfect. Ellipse is kind of an ugly object. Now, it can be any shape. These days, we thought that the heavens were perfect. Life on Earth was a big mess. And the heavens were ruled by perfect order. So he himself writes in his diary, I'm bringing in a cart full of manure into science. But of course, sometime after, Newton showed that in fact an ellipse is beautiful. All the orbits are beautiful because they're all so-called conic sections. So there's great mathematics hidden in it. Now, I won't show many equations, but I want to show you one equation. If you've seen one, you've seen them all. A equals B. That's the typical format of a mathematical equation. I want to point out a very important symbol that's overlooked often. That's the equal sign in the middle. It's the magic in the equation. The equal sign connects two different worlds, world A and world B. Think of E equals mc squared. Energy related to mass. It's a miracle. Philosophers call this principle, the importance of the equal sign, Clinton's principle, because, you know, there's this American president who once said, you know, it depends on what the meaning of is. It's a crucial step, and the few examples I will tell you are about connecting two worlds which were basically not expected to be connected. And to see whether you have any kind of how you think of mathematics, I want to do a little experiment, so I want you to look at the screen intensely. Did everybody see something? So now I ask you a question. Was the triangle above the circle? Research shows that in half of the cases, people say, well, I remember the image, and where was the triangle? Was it above? No, it was below. The other half, immediately when I say a triangle above a circle, sees an image of a triangle above a circle, and then says, well, wait a moment, the mental image is not the same as the image I see on the screen. People of the first category are people who think basically with the left-hand side of the brain. They think in terms of language, and analyzing language and order. These are people, if you want to give them the directions, you have to say left, left, right, left. The other one think geometrical. They think in terms of images, not text, but images. They're much more helped if you draw a little diagram how to go. Mathematics is exactly the same. One part of mathematics deals with algebra. That's kind of logical steps, basically doing things in time. The other half thinks about geometry, something that you can walk around, more space instead of time. Now, if you think about it, our universe also has two sides to its brain. Large structures in the universe are described by general relativity, about curvature of space and time. That's geometry. The small world of elementary particles is described by algebra, by quantum mechanics. And these, in some sense, have to come together. You know, in some sense, you can say there are two ways to do this. One way is to look at the macroscopic world around us. And so where can we find mathematics? So one school says we find mathematics at the smallest structures. By reducing everything to little building blocks, we find beautiful formulas to describe the big mess around us. So for instance, I'll give examples where we find some algebra that we pull out of geometry using quantum mechanics. Another school says, no, 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 no. If you want to find beautiful structures, you shoot at the large structures. If you think of a glass of water as billions and billions of little molecules, you will never discover the beautiful laws of hydrodynamics and the properties of water. So we will see also examples where beauty is in the large structures, and it emerges out of kind of chaos and small stuff. So there are two kind of brands of mathematics, two kinds of aesthetic feelings you can have applying mathematics to the real world. Now, if you live in the world of elementary particle physics, you have to explain pictures like this. And that technical term is kind of garbage. You know, this is just coming everywhere. And is there mathematics in that? Can you calculate these objects? And during times, people have had mixed feelings about that. In the 1960s, people thought, well, perhaps there were so many particles around these days, hundreds and thousands. Perhaps nature is a black box, like how most of us think about technology. You know, something comes in, something goes out. You won't repair your own iPhone or something. A black box that couldn't be opened. In fact, at one of these days, Freeman Dyson, he gave a lecture here as a very distinguished professor at my institute. He said, I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. Quite harsh words. The remarkable thing, as he was speaking, early 1970s, it turned out that the black box could be opened, and in the black box was a tiny, tiny formula. Here I use the full power of mathematical symbols to write an equation of the standard model of elementary particle physics in terms of a single equation. I can lecture about this equation to a mathematician and explain her or him every symbol, and they will say, yes, I understand. These are elegant mathematical structures. These are things we study anyhow. Now, this is not the way you learn the formula in college. In fact, this is the way you get it, written in components. That's just to kind of bring home the fact that this is a serious business. But on the other hand, actually can put the whole standard model on a t-shirt. 16 particles, now 17 particles with the Higgs, that explain everything we see around us. And in fact, most of these particles don't even play a role in our present situation. They were very important in the very early universe. Beautiful equations that describe all this. Isn't it amazing? Why is that formula not on every street corner? And the amazing thing is that it describes the world not by giving very precise prescriptions, but basically by giving probabilities, a chance that something can happen. Particle can go straight through, they can exchange a particle, they can exchange 2 particles, or 3, or do something much more complicated. And the mathematical formulas allow you to compute the probability that this will happen. And these numbers are among the most precise predictions and verifications in all of science. Some of them into 12th decimal. That's the distance of a hair, measuring the distance of the moon to the Earth within a hair width. Absolutely amazing. It's really the small particles in some sense where we have great confidence and understand things. Now, to understand the role of mathematics, we have to go to something painful, which is extra dimensions. And I will actually, they will come several times in this talk. And of course, we go to Einstein, who famously said, time is the 4th dimension. Now, thinking about higher dimensional spaces is difficult. So I have a little exercise here for those of you who are afraid of extra dimensions. So this is 2 dimensions. That's a square. And you can think, well, how would a square look in 3 dimensions? Well, it looks like this. So you can admire my animation. I actually was thinking perhaps I should have brought you a 3-dimensional cube. But you see, even if I had a 3-dimensional cube and was rotating here, you would still look at something 2-dimensional because you are looking right now at the retina, at the back side of your eye, which is totally flat. Everything you see is 2-dimensional. The 3rd dimension you kind of construct in your mind to interpret moving images, like this animation. So here is a 4-dimensional cube. So perhaps we can all look at it, and perhaps some of you in your brain will say click, and you will see the 4th dimension. I actually had a colleague who was a professor of biophysics, who for a full year with stereoscopic views looked at pictures like this, manipulating them, etc., hoping that something would say click. Well, a lot of things happened to him, but he didn't see the 4th dimension. You know? But perhaps he should have tried it for 2 years. I'm always looking for a volunteer here. In fact, another way to think about this is more in terms of time. So here is a movie. And of course, the fundamental idea of Einstein is if you have a movie, it's a collection of photos, of images. Take these images and stack them on a big pile from bottom to top. So you're going up in the stack, you're going kind of moving in time. And a single particle, you see here the red and the green particle, which are rotating around. In space-time over here, they become these strands, these strings that go up and down. And that's the language in which modern particle physics thinks. Space-time diagrams. Now, this can actually be used to answer some deep questions. And one of the deepest questions that perhaps not all of us realize physics has answered is the following question. Now, you learn about electrons, and you can read about the mass and the charge of electron. But is every electron exactly the same? Is there a factory in the universe which makes perfectly identical copies of electrons? How and why? Why is there never one which has a little scratch or something? So this is a deep question, and there's also, you can time, you know exactly when the beginning of the answer was formulated. And there was a telephone call in the early 1940s between John Wheeler, famous physicist, inventor, worked on the hydrogen bomb, invented black holes, worked on many, many areas in quantum mechanics, and his then graduate student, Richard Feynman. Feynman actually in his Nobel lecture explains this telephone call. It was Saturday night, And so your advisor is calling you in the middle of the night, and Wheeler says, I know why every electron is exactly the same. Because there's only one electron in the whole universe. Okay, please explain. This was the image of Wheeler. Here's our space-time. There's the electron. Now, usually it should go up in time. We are all going up in time. It's no way in which we can do that. But suppose that I could go back in time. Or back in time, go walk in, come up to the stage and stand next to me. There would be two identical copies of me, right? I could do it another time. Would be 3, would be 4. So Wheeler said, suppose that particles not only go up, but also go down in time. And they could go up and down and make this big, big knot. Suppose you would take one of these slices, one of these pictures, and you would do it somewhere in the middle. You see many, many electrons going up and down, positively and negatively charged particles. They would have exactly the same properties, because they're all the same electron. So that was his theory. Well, Feynman said, well, why are there more electrons than anti-electrons, and blah, blah, blah. But these particles' trajectories are now called Feynman diagrams. In fact, after the war, Feynman actually started to work with this. And this is a beautiful picture of one of his notes, where the first time he was thinking about sending these particles back in time. You see, here it's doing these particles going up and then it's going back. And he noticed that by sending them back in time, they exactly are giving the properties that we wanted. So in some sense, he really ran with the idea. And in fact, he was drawing these beautiful diagrams, Feynman diagrams. And Feynman is describing, he's making diagrams while everybody else is doing difficult computations. He hoped one day, perhaps all the physics magazines and journals and books would be full of diagrams instead of formulas. And he's right. That's actually the case. In fact, some time ago, a young physics graduate student was walking in LA and saw this van. And there was a lady driving the van, and she stopped at the red light. And he noticed that there were all these Feynman diagrams on the van. So he stopped and said, well, Mrs. I really have to tell you that the symbols that are on your van, they actually mean something in physics. They're called Feynman diagrams. She said, yes, I know. I'm Mrs. Feynman. A beautiful picture also of the Feynman family with the van, you know. In fact, it's even more crazy. Particles are not going up in time. They can, for instance, split, make a little detour and go back. You know, this is the fundamental principle in quantum mechanics, that basically anything can happen as long as it happens fast enough before you can detect it. I always feel this is the principle that Dutch society is based on, you know. We are kind of genetically favored to understand quantum mechanics. And in fact, you can even have this funny thing, but out of nothing, a particle and antiparticle are born, and then they annihilate again. Or, as Wheeler would have liked it, a particle going up in time, back in time, and that's kind of closing the loop, making these endless loops, just in vacuum. In fact, vacuum is full of these particles that are created and annihilated again. That's what we call the vacuum energy, and certainly you must have heard in talks here about dark energy, the energy that's inside empty space-time of our universe, and it must have be a reflection of all these crazy processes. So what has this to do with mathematics? I want to bring you a mathematical problem that mathematicians have been struggling with for centuries, and that's understanding knots. Now these are knots which are embeddings of circles in space, so not a knot that you tie in your shoelaces because you can unknot this, but you tie somebody's shoelaces and then glue the two ends together, you know. That's actually kind of silly because then you never can untie your shoe, but that's the whole idea. So, and how many different ways can you do this? If you're allowed to move the knot around, but not to break it. Is there something like a big book of knots? And there is. In fact, there's an infinite number of knots. And we know if there would be something like an alphabet for knots, even to order them, like you order names in a telephone book, the alphabet would have an infinite number of letters. So it's one of the really most difficult problems in mathematics. And to understand how difficult it is, that till the 1980s, of this infinite amount of letters that you should use to describe them, only one was found. Around 1920, not a second was found. So difficult is it. But then it was solved. It was solved using physics. And you will now appreciate what the physics solution was. Because people said, let's look at a knot like Wheeler or Feynman would look at a knot. They would think of this as a particle moving in a space-time, a funny space-time, because it would have two space dimensions and one time dimension. So two spatial dimensions and time pointing up. And it would be a particle going up and down in space-time. And it would be something that could possibly happen. And the rules of quantum physics will give a number to this process, which is the likelihood that it can happen. So there could be like a 0.7% chance of this process. So you would associate this number to the knot. And in fact, you can go around, and if many things can happen. You can send a quark around, and then you can have a process where this will be a Feynman diagram where you 1 particles interchange, the gluon, or 2, or 3, or 4. So you can use all the Feynman diagrams to describe all the knots. In fact, this is so successful, this program, that within 20 years, 10 years, it led to the conclusion of this program, and the mathematician Konchevich, who basically got the Fields Medal. You know, there's no Nobel Prize in mathematics. There's something much more difficult to get, which is called the Fields Medal. It's only awarded every 4 years, and you have to be under 40. So it's like with the Olympics, you can peak wrong. Like Andrew Wiles, who proved Fermat's last theorem and turned out to be 41. So bad, and too bad, Next life. My second problem, actually, that I want to deal with you is even more, in some sense, more elementary. It goes down to the purest form of mathematics, which is counting. Kronecker, the German mathematics, famously said, God created the integers, 1, 2, 3, 4, 5. All the rest was human efforts. It's very important to realize that mathematics is what mathematicians do. Now you can walk around everywhere, but you will never find a mathematical equation carved in the wall or something. It's just impossible. I must say I had one experience, so I have to tell you a little anecdote. I was walking in beautiful woodlands, and suddenly I saw a sign. And the sign had the equations of particle physics there. In fact, it had the equations of string theory in colors and symbols. It was standing there right in the middle of the woods. So I thought, what is this? Is there some divine intervention? And then I noticed that there's a castle close to the woods, and it was bought by the Maharishi University. And and they had a certain program, and they embraced the laws of physics, so they put these signs in the woods, so people would actually look at it and perhaps be inspired. But that's the only time I actually found a formula in nature. Usually you have to write them down yourself. Quantum manometer geometry. And that's actually a field which is very respectable in mathematics, but sometimes it's also frowned upon as being kind of a little bit recreational mathematics. Now it's just counting things because just to show off what you can do. And but actually now it has a very different status, and it's, among others because of the element I want to tell you. So for instance, here I've drawn, it's very difficult, it's actually a 6-dimensional manifold, or it's 3 complex dimensions. It's given by the solution of what's called the quintic equation. So it's this equation over here. It's a little bit like the formula of Pythagoras, a squared plus b squared is c squared, but then with 5 powers, and not 3, but 5 of these elements. So this is a beautiful equation, and the wonderful thing is it slices out the space. The space is 6-dimensional space. And the 6-dimensional space called the Calabi-Yau manifold is very special because it's one of the rare spaces that allows a solution of Einstein's equation, but yet it's compact. It's like a sphere or something. So it's the analog of a flat sphere, but then in 6 dimensions. It's a beautiful space. And mathematicians like it because they can count things on it. For instance, they can count curves, as they call it. They count curves of degree d. Now, I'm not showing you many equations, but for those of you who are interested in it, it's basically the following. You have your 5 variables, x1 to x5. Each of them is a polynomial of a certain degree d in a single variable z. So it has all kind of coefficients, a1d, a1. These coefficients are all unknown. And you have 5 of these polynomials, 5 set of equations with all these coefficients. You plug them in the equation, try to solve for the coefficients a, all the a's over here. And if you figure it out, you see there are as many equations as variables, so there should be a finite amount of solutions. Clearly, if D is larger, you get more solutions. To give an example, one number every algebraic geometer knows is the number 2875, because obviously that's the number of lines on a quintic. So the lines is degree 1 curves. It's a classical result obtained in the 1880s. The next one is conics, already much more complicated. These are conics, like circles, parabolas, hyperbolas, and there are already a large number of them, 609,250. And that was found in the 1980s, and using the full power of modern mathematics. So the next step would be the number of cubics, curves given by a cubic equation. And there are 370,206,375 of them. Now, there's a funny story about that number, because mathematicians tried to compute this, wrote a massive computer program, got a number out. In fact, physicists asked them, can you compute? So they started writing this big program, code after code, got a number. Come back with the number to the physicist, and the physicist said, are you absolutely sure there's not a mistake in your code? Okay, they went back and checked, and indeed there was a mistake. And so they came back, so sorry, you're right, thank you for pointing out, this is the number, 370 million, blah, blah, blah. Yeah, the physicist, that's right. So, okay, well, wait a moment, this was a massive effort, all the great minds, endless computer time. What did the physicist have? Well, the physicist had a little list, and this was the list. They had all the numbers. So just imagine, that you take a century, go from 1 to 2. It takes the massive advent of computers to go from 2 to 3. Going from 3 to 4 is like the Large Hadron Collider of mathematicians. You wouldn't do that. And then certainly all of them are there. It's very difficult to convey the emotion this brings to a mathematician. This is like you're not just beaten to one result. It's like your whole life doesn't make sense anymore. Apparently, you're doing something completely trivial. Where does all these numbers come from? And these beautiful, beautiful numbers. Well, here's the story. It has to do with string theory. String theory is a generalization of particle physics, where instead of single particles, we think of little vibrating strings. Well, there are a lot of things to talk about string theory, but in the mathematics, it really has beautiful, elegant structures. In fact, you can look at the movements of strings. And if a string would move, just as little particles would give these kind of spaghetti strands, these kind of knots in space-time, a string moving in space-time gives a two-dimensional surface. Or you can think of it as a complex curve, using the language of complex numbers, which is really what mathematicians like. So they think of this as a complex curve. And so, or a Riemann surface. And if you somehow, you can think of these are, instead of the Feynman diagrams, we have kind of Feynman diagrams on steroids. So they're not like one-dimensional, they're two-dimensional. They're like fat, thick Feynman diagrams, they're Riemann surfaces. And what you can do if you want to, so that's the first element. The second element of string theory, it has many extra dimensions. Not just space and time, which makes 4 dimensions, but it has so-called internal dimensions, that small dimensions that are curved into each other, in fact 6 of them, and in fact curved in a way that they satisfy Einstein equation. And so Calabi-Yau manifolds, or this quintic in particular, could be the internal space of string theory. So basically, of every point in space and time, there is this internal manifold curved into itself of tiny, tiny dimensions. So string theory is quite interested how a string moves in that space. And in fact, it is that the shape of that space that in string theory would relate to what we found on our T-shirt, the standard model of elementary particles. In fact, adding loops and handles to the space, the Calabi-Yau manifold, means adding particles and they're changing their properties in terms of the 4-dimensional physics. So not only string theory studied these spaces, but he also studied the movement of the strings in these spaces. Now I said the string is moving around, so it's doing something very naturally. It's doing what we call the sum over histories, the fundamental law of quantum mechanics. In quantum mechanics, you don't have something happening, everything happens at the same time, only with varying probabilities. If you leave the audience, the lecture hall tonight, you will go through the door, I hope, and just enter to the street. There's a small probability you go through the wall, and I think none of us will actually experience this because we're not elementary particles. This is just almost zero probability. But it's a very small chance. And so these numbers can be computed. And in fact, they belong to the most precisely computable numbers in physics, in particular in these kind of mathematical settings. These numbers can be computed exactly. And in fact, if you compute the numbers, you get all of them. The coefficients, this list of numbers I showed that kind of totally took away the mathematicians, they're just the coefficients in this formula here. They're all together, they make up one nice thing, which is the quantum mechanical amplitude, what is the probability of a string moving in that space. Now, this gives it a context, but didn't yet give a solution. There's another thing the physicists did. They looked at what kind of spaces do you have. Oh, you have the quintic, but are there other manifolds? Because they want to study physics, so they want to say what kind of possible worlds are possible within string theory. And what they do, they make a plot. They made a plot of all the possible spaces that could appear. And they noticed that there's a beautiful symmetry in the plot. Now, it's kind of left-right symmetric. So for any space they could find, there was like a mirror manifold. There was a manifold that shared some of the properties, but was fundamentally different. Had different geometry, different properties, different particles, but they were like paired in this deep way. And it turned out that in particular for this quintic that all the mathematicians were interested, there was a candidate for the mirror manifold. And if you knew the mirror manifold, the calculation, this very difficult calculation, but namely finding all the numbers n, could be translated in what was an easy complication, an easy calculation, by the way, on the mirror manifold. So this kind of sounds like magic to mathematicians. Like, okay, well, first of all, you sum everything up to a big formula, and then hocus pocus pos, there's a mirror manifold, and that actually captures all your formulas, and this is the answer. But clearly the numbers were right. And in fact, what happened is that mathematicians, just as with the knot invariants, they took this idea and they said, let's try to prove this. Not by kind of constructing all of string theory and physics. No. They take the hint, they take the formula, and they prove it in their own means, using everything. Now that they know where they were heading, they were actually able to make the proof. So this is now an essential part of geometry. And it's done, it's proven in a mathematical way. The final subject will have to do with something which is absolutely crucial to modern physics, and also very dear to the heart of any mathematician, which is symmetry. Actually, going back to the old Greeks. One of the amazing things is that the Greeks were so fascinated by these symmetrical figures, yet they didn't invent group theory, which is the modern language we use to describe symmetry and the application of symmetry in the real world. Now, again, symmetry is crucial in our understanding of elementary particles. You might have heard that particles come with all kinds of properties. Like, for instance, quarks, they have colors. They have 3 colors. There's red, blue, and green. Of course, it doesn't mind. It's just a name. They not really have visual color. But it's a good word, because if you think about how you perceive color, say on your television screen, you think of how the pixel is colored. It's actually made a color by actually getting green, red, and blue light to you in certain proportions. If all 3 are absent, it's black. If all 3 are maximum, it's white. And you can make all the other colors into it. The moment you're picking a color, you're moving in a 3-dimensional space. Now, a quark is also kind of moving in a 3-dimensional space. You can think of a quark as having a little arrow that's pointing in some space, color space. And if the arrow goes around, it kind of changes its property. And the theory is that quarks are continuously doing this. Quarks, as they are tied together with 3 of them in a proton, for instance, are continuously exchanging their colors. These kind of arrows are wiggling. In fact, there is a kind of a field of quarks. And I hope, again, you admire my PowerPoint skills, because this is one way in which you could think of this. This is just like the Calabi-Yau space. It's everywhere in space-time. Actually, as we speak, there's this quark field permeating every nook and cranny of this lecture hall, in fact, of the whole universe. And so there's a symmetry where you could rotate all of these, but this is not what happens in nature. This, I would say, is really a kind of a communist way to move. Nature is much more liberal, I say. So every space point is free to move in its own individual way. And so there's a huge symmetry, because you can take any space point and in any point of space and time and move around the direction of the color of your quarks. In fact, it's these kind of waves in these fields that we in the end see as gauge fields, as for instance the photon would be the example for light, but in this case for quarks we call them gluons, which are the force-carrying particles of the strong nuclear force that holds the particles in the nucleus together. In fact, in using the laws of Feynman diagrams, something like this happens. You have a red quark and a green quark. The red quark and the green quark, they come here and then they exchange color. So the red becomes green, the green becomes red. And they do it by exchanging this gluon, which has two colors, red-green. So it's a particle that can turn a red quark green and a green quark red. And so if there are three colors, you can imagine there are 9, 3 times 3, of these gluons. Well, there's a small detail where they're not 9 or 8, but I won't go into this detail. But that's actually what happened. There are 8 of these gluon flavors. And in fact, what they do is actually they are the particles that make these color changes possible. So how is this again related to modern quantum physics? Well, again, string theory comes, so to say, to the rescue, or gives a totally different way of thinking about this. Now, you see, another picture is that, I talked to you about extra dimensions, but the extra dimensions can be of various kinds. For instance, a certain physical model where our 3 + 1, so 4-dimensional space-time, is like a flying carpet, floating in a much bigger dimensional space. So there is an extra dimension, but you can't reach it because you're kind of tied down to this flying carpet. Now, one of the ways in which that carpet could have extra structures is not one layer, but it's many layers. If I would give an old-fashioned talk with plastic transparencies, you could have like 2 or 3 together. You wouldn't even notice. So you can have various of these sheets, and you could pull them out. Open strings would actually be attached to these strings, and you could pull them apart. You would see that the string is attached from one sheet, and it goes to another sheet. So actually, you should have given them colors. You could have a red, blue, and green sheet, and the red-green gluon would be something that would connect the red to the green sheet. In fact, you get a natural way, a matrix of, so to say, open strings, which is a very elegant way to describe gauge fields in using this language. And in fact, if this thing would break apart, it would break apart in 2 of these open strings, which are always be connected to the same kind of intermediate point. So you would have the rule of matrix multiplication, which is the essential way to understand the symmetry groups of nature in a very, very simple and elegant way. Now, why is this again important? Well, it's important because all of this is quite essential in our modern way of understanding black holes. So black holes in string theory, it's again a long story, but what we'll do actually, the closed strings will actually curve space and time. But you will have a black hole, the black hole will have a horizon, and the things kind of living on the black hole horizon are these open strings. So in modern language, we find gauge fields, or we find basically the analogs of quarks and gluons on the boundary of this black hole horizon. And that has very, very important implications of our understanding of space and time and how it all kind of fits together. I would say this third example is something where it's more difficult to point out to the kind of formulas that would sweep mathematicians away, but I'm sure they will be coming. And there are already a few of them. And that's actually one thing that is being a continuous pattern over the last kind of decades. What we have seen is that like physics and mathematics are in some sense speaking different languages. And what we're building a dictionary where the elements in mathematics have a physical implication. I can draw nice diagrams and figures, and the same figures and diagram end up also as mathematical formulas. But in some sense, you weren't aware you're describing the same stuff. I think one of the great things that physics is doing in this context is putting mathematical problems in their natural context. I think that's something that, mathematics is, of course, much more ambitious than physics. two famous sayings. One is that reality is a first approximation to mathematics. I like that one. And second one, there's a famous story where a mathematician was describing to a large audience what the difference was between physics and mathematics. He says, well, physicists describe the laws that God has decided that nature should obey. Mathematicians study the laws that even God has to obey. And a typical mathematician will feel that they're not bound to reality, so they can go in any direction. But time and time again, we have seen that putting things in a physical context is extremely useful for the development of mathematics. In fact, you can say that in some sense, every context enriches a mathematical concept. Famous mathematician who unfortunately died much too young, Bill Thurston, has written a beautiful article about the use of proof in mathematics. And he comes with a simple example. He says, suppose you have something that everybody learns in any calculus course, which is the derivative. Now, if you go to a university math course, you get a definition with epsilons and deltas. It's pretty complicated. And he asked the question, is this the right way to understand derivative? And then he goes on and gives other definitions. He says, one, velocity. Now, we all know the physical experience of speed. And we know we can move, we know what it means to go 50 kilometers per hour only for 5 seconds. That makes sense. It takes some time to get used, but we understand this intuitively. And we understand that our velocity can also have a direction. We can move in many ways. Then it comes definition 2. Think of a slope. Now, you can think of a slope as a very beautiful way to think of a derivative. You can see why you can have a slope in a mountain, so it has 2 directions. Or you can think of it as an algorithm. Those of you who are familiar with calculus know that x cubed, if you differentiate, it becomes 3 times x squared. You can do that with other things than numbers. You can think of it as an approximation. Think of it as a linear approximation, or think of it looking through the microscope. And Thurston goes on, and certainly he has definition number 37, which is very complicated about some principal bundle and a flat section, and I won't bother you with the details. But he said, once I needed definition 37. And then he makes his point. He says, what we think of our key ideas in mathematics, they come alive because they have so many applications and contexts. And it's actually that what actually makes mathematics so powerful. It's these kind of tools that have this unreasonable effectiveness. Now, mathematicians are very neat, so they kind of clean up their toolbox. They say, well, this is geometry, this is algebra, this is number theory. But then a simple-minded physicist comes, and he just wants to solve a problem. Now, and he goes to look in the toolbox and takes whatever he wants, and just, hit it and try to crack the problem. And then certainly it noticed that certain mathematical problems actually come together. So can that physical intuition be taught? Should you take any mathematician and say, well, first, be trained as a quantum physicist, and then become a quantum mathematician? Apparently it doesn't work. It's almost very strange that it seems to be that mathematical rigor and logic and physical intuition are in some sense complementary and very difficult to have at the same time. None of the problems I described today have been solved by making the physical intuition more rigorous. It was basically a path that was too long and winded and overgrown, and nobody wanted to go there. It's good for intuition, but actually the proof was done in a very different way, using the skills and intuitions of mathematics. So perhaps it's, again, the left and the right-hand side of the brain kind of in conflict. And finally, there's another point, which of course physicists are very much aware, that all this mathematics is extremely beautiful and tempting and seducing. Now, and sometimes, like Odysseus, they have to tie themselves to the mast of the ship, not to be seduced too much by the beautiful mathematical formulas. Because it's not obvious that everything that I described today is actually describing nature. But it could, in a very kind of indirect way, of course, be. And it's certainly kind of all hangs together. And in fact, going back to the very first part of my talk, where I told you about Plato, who had this idea that the dodecahedron, the fifth element, could be described the world outside the Earth, which we now know there's no need to. We actually know with great certainty that the physics at very distant stars and planets is the same physics that we are just finding here on planet Earth. Actually, Plato had something happen to him which typically for a theorist. If you look in his text, he writes, it's only a suggestion. Don't take this too serious. Later generations took this extremely serious, and then it became a canonified theory. It was just a suggestion. As a theorist, you try different ideas. And of course, Plato had a good image for that. He had this famous Plato's cave, where there are two worlds. We are kind of the prisoners in the cave who can only watch the shadows on the wall of the cave. But somewhere up there, in the Platonic realm, are the pure and perfect mathematical figures. And so it's the poor shadows of these objects that we are struggling with. Like, I can show you a picture of a dodecahedron, I can show you an artwork of a dodecahedron, but none of these has the absolute symmetry that it would have in your mind. It's only the Platonic concept which really has the perfect symmetry. But the crazy thing is that in these days we are living in kind of the upside down Plato's cave. It's more physics in some sense that's kind of up in the air and has very grand ideas and complicated extra dimensions, strings, brains. It's all there. It's perhaps a dream world. But the remarkable thing of that dream is that it's projecting shadows, very precise and clearly defined shadows, in the form of mathematical equations and conjectures, that mathematicians then kind of take and work on and prove and enrich mathematics by it. So I would say actually this dialogue, this divorce that was pronounced by Freeman Dyson, I think it's, I would say the two have really fell in love again. It's a very intense period of the interaction between mathematics and physics, and seriously, I think, looking back in this time, I think it's a golden age for the two fields. And I think it's one of the intellectually most stimulating and exciting phenomena in modern science. Thank you very much.
Thank you very much for an extremely accessible and interesting and highly visual and even humorous lecture. That was outstanding. Thank you very much. We're going to open up the floor to questions now. So if anybody has a question, and please don't be shy about that, please raise your hands. Our microphone runners will come down to the front of the hall here. Please raise your hands high. We'll find you and ask you to stand up and share your question. Here's one right down here on my left. So we'll start right here. Thank you.
Good evening, Doctor. So a question I have is that what you talk about, this effectiveness, this has happened numerous times in history, like, for example, abstract algebra, group theory, the development of it. This has, physics applications in form of mathematics in the 19th century. So, I mean, are you, like, the theory you're advancing, I mean, is that, like, something recent, or because it seems to be like happening continuously throughout history, like physics? And
you're quite right. So there were, I think, there were periods of. Thank you very much for that question. There have been periods of ups and downs between that dialogue, and clearly, now the 17th century was absolutely spectacular. But what I think is perhaps the most unreasonable of this, that if you think of almost all our mathematical concepts, geometry, calculus, they all have come from our everyday experience. It's our brain. Our brain has developed over hundreds and thousands of years, dealing with stones and branches and just the laws of nature as they apply to ourselves. We have never lived in the world of quantum mechanics. So the fact that we, with our brain developed at room temperature, can go to these extreme circumstances of the very small and high energy of the very large, and that our mathematics is still working, more than that, I think, that it's even kind of enhanced, that the kind of mathematics that is relevant to these realms is even more powerful than the one that describes classical mechanics. It's not obvious. For instance, I think in the 1960s, where people were seeing that the world of elementary particles is this big mess, Just if you look at the, for instance, the data of ordinary, I mean, some of you have perhaps seen the particle handbook, which describes all the elementary particles, and not the 17 of the standard models, but all the other ones. It's, I think, a 1,000-page thick telephone book, you know. So it's not at all clear that this is being described by a handful of equations. So I think that is not to be expected. But you can at some point perhaps draw a lesson. And one of the lessons I draw is that nature likes to work in this way. She's kind of fond of equations. So famously said that, I guess Darwin, that she's fond of beetles, you know, there are many, but also equations. And no, we never know. You could run out of luck, and perhaps at some point we do. But it's extremely powerful that in the shortest distance that we have done measurements and the largest distance, we have very simple equations describing this. And I don't know what's unreasonable. Afterwards, it's perhaps a tautology. You say, of course, it's described like this. But let me say there were points of existential fear that our luck would run out.
Thank you. Another question over here, and a reminder, show of hands anywhere in the theater, and we'll bring a microphone to you.
Do you think that because of the other exchange particles, the patterns they have with the string theory, do you think you could prove whether the graviton exists?
Well, it's a kind of a difficult question. Because in some sense, you know, I think actually there's kind of a different kind of proof which you mean. It's really kind of finding the experimental evidence for gravitons. And I think actually we'll see a lot of evidence, indirect evidence in cosmology, but actually detecting a graviton, you know, with a classical graviton, we'll actually need a gravity detector, gravitational wave detector. That are being built. I think there's a very powerful theoretical argument that they should exist. You know, we see indirectly there are waves of gravity, just as we see electromagnetic waves. We know that these waves come in energy which can be smaller and smaller and smaller. At some point there will be kind of a quantum theory will say there will be minimal packet of energy that you can store into it. So I still find it very difficult to avoid the concept of a quantum gravity wave, so a graviton. I think actually in terms of the mathematics that's involved, it's actually in some sense pretty straightforward. It's you know, it's just by analogy of the photon. So I don't think that we need to solve very difficult mathematical problems there.
Thanks very much for that question. I'd like to follow up on that with a question emailed in here. And it's actually a beautiful segue to our next public lecture next month. And the question was, what sparked your love for science? So maybe you could take a few minutes on your journey from elementary to high school to post-secondary, and how did you come to be the mathematical physicist that you are?
Well, I was actually quite late, and I think quite many people are quite late to mathematics and physics, because of course you got it at high school, but I never realized that this was just the tip of the iceberg. In fact, the first time I really realized this was, I think I was like 11 or something, and somebody gave me a book about a very different topic, about DNA and genetics. So I still very vividly remember reading the book, and it was kind of crystal clear. And I felt there was a big conspiracy out there that prevented me from knowing this. So I ran into the kitchen. My mother was cooking and said, "So this is just a disgrace, you know. This is how we work. Nobody told me." And this is basically the first thing you should learn in elementary school. And in the same way, I'm still upset that people think if they want to teach physics to young children, that has to be of the little things that are around you or something. I think you should know that the world is made out of atoms. So that there are elementary building blocks of the world. It's the most fundamental thing. So I got into that. I think it's only when I was like 15, 16 that I started to discover not only that I was this kind of you know, went kind of naturally, but also that there was a whole world around. And I think some of my high school teachers were extremely helpful. In I know I got an old mathematical encyclopedia. And in some sense, still think very fondly of these days where you weren't taking any official classes, you were just figuring out yourself. I think that's the greatest pleasure of being a physicist or a mathematician. I think you can just need just a piece of paper, and you can just work yourself.
Thank you for that.